Okay, let's continue. And here are some very quick questions just to make sure that we are on the same page. And what is the median of a list? So what is the median? The median is if we sort all the values from low to high, and then whatever in the middle should be the median, right? And then the next question, what's the difference between the median and the average of the same list? So what's your answer? Okay, and then how about we move on and answer the next question? If we add one more really large value to the list, does that change the median? What's your answer? The answer should be yes, but probably the median shouldn't be changed a lot. And if we add one really large value to the list, and then does that change the average? And then probably yes, and it could be significant change. And the reason is, let's assume that we all live in the same community and we are all normal people, working class family. Okay, and then our median of this household income should be a reasonable number. Well, and all of a sudden, for example, Elon Musk moved to our community, and then his household income is really large compared with us. So that is the really large value. And then does this person moving into our community is going to change the median of the household income? Probably not too much. But does this change the average of the household income? And the answer is yes. And if we look on the average, and it seems that this is a rich community, but the answer is no, it's not correct. Those people are all ordinary working family or working class families, and they just have a really rich neighbor in that neighborhood, right? And then the next question, how do we get the median of a list given the algorithms we know? We have been talking about the sorting algorithms a lot, right? So how do we do that? We just sort out the values, and after we sort the values, and then we go and grab the middle value, right? And that is the median. Okay, and then let's see what is order statistics. So in our textbook, the ith order statistics is a set of n values is the ith smallest elements. Okay, so when we talk about the sortings, and probably you have already noticed that in our textbook here, we always use the sorting from low to high. And then if we want to get the first order statistic, what is that? That is from low to high, and then we grab the first value, and that is the smallest value, which is the minimum, right? And then how about the maximum? The maximum, if we know there are a total of n elements, and then the nth order statistic, that is the maximum. Okay, and then how about the median? The median is n divided by 2 order statistics. And the next question is, what if we have 2 median? And then what do we do? And in some of the other textbook, and they may tell you, if you have an even number of the values, you are going to grab the middle two, and after you have the middle two, and then you average them, and then that is your median. But in our textbook, we do that differently. The median if we have the n as an even number, and then we grab the middle two value, and those two values put together, they are the median, or we have two medians. Okay, and then how do we calculate the order statistics? We are not talking about just the median. We can do the 10th largest value, or the 15th smallest value, and those are all order statistics. So how do we find the order statistics, and how do we make it happen in a reasonable running time? Okay, so let's talk about the max and min first, because the max and min are the easiest cases. Okay, so if we have a list, how do we find the minimum? That's easy, right? So if you don't use the built-in max or min, and then you just grab the first value, say in this case I grab the first value, and I assume that it is the minimum, and then I visit the rest n minus 1 values from 5 to 31, and then for each value I compare that with what I'm holding using my hand right now. So, and if the current value, say 5, is even smaller than the value I'm holding, which is 4, and then it will be the new minimum. And then I move on and visit 11. And then if 11 is smaller than the current smallest value I'm holding, and then I'm going to update the current smallest value. So this is the way that we find the mean. And similarly, well, we can tweak the code a little bit differently, and then we got the code to get the maximum. Okay, and then the next question is how can we find the minimum and the maximum with no more than twice of the cost? Well, the easy way would be, okay, I use one hand to hold the max, I use the other hand to hold the mean, and then I'm moving those two cursors down. So when I move on to the new value, I do two comparisons. So for this value, hey, are you greater than the max? If so, I'm going to update the max. Are you smaller than the mean? If so, I'm going to update the mean, and then I move the cursor down. So if you're doing this way, and you are exactly doubling the cost, because you're doing two cursors, and for each of the value, I'm doing two comparisons, right? So can we do that better? And the answer is, here is a very, very smart strategy, and say, well, to start this algorithm, we grab the first value and then 4. I'm assuming that 4 is the current max, 4 is also the current mean. Okay, and then for the next pair of values, I first compare the 5 and 11, and 11 is greater value. So for the next pair, 11 compare with the current max, and the lower value 5, the 5 compares with the current mean. Okay, so this means there's no point that I compare 5 with the current max, because 11 is greater than 5. And similarly, I don't want to compare 11 with the current mean, because there is a smaller value 5 there. Okay, and then if we count how many comparisons we are doing, so for the 5 and 11, this pair, I do one comparison between 5 and 11. And then for the greater value, I compare that with the max. For the lower value, I'm comparing that with the mean. So for each pair of the values, we do 3 comparisons. So this will be all 3 and divided by 2. So you may say, does that save anything? And the answer is really no, because it is still a linear time algorithm. However, this is a kind of a smart implementation. Even though when we are coding algorithms or designing algorithms, sometimes we don't save anything, but we are putting in some effort to optimize the algorithm. It's always a good thing. Okay. And well, let's move on to a harder topic. How do we find other statistics? I mean, not the largest, not the smallest, and then how about the 10th smallest value, and how do we do that? And this problem is called selection. So we are trying to find the ith smallest element of a set. And in this class, we are going to show 2 different algorithms. Number 1, this is a practical randomized algorithm with ON, expected running time. But in the worst time, it's not ON. So it's kind of similar to the quicksort. It seems that, well, if you look at the worst case, and it's not impressive, but well, in the general case, and it should be good enough. Okay, and then later we are going to see another algorithm, and that algorithm is really tricky, hard to understand, but that is a really, really smart algorithm. Well, and when I first learned this algorithm, I find, I hate that. It's really hard. But well, when you see that a couple of times, and when you really to give that a deeper dive and see the design, and you will see how smart this algorithm is. Okay, so let's start from the first one. That is a randomized selection. And the idea is we are trying to use the partition from the quicksort. Okay, so for the quicksort, what's the cool thing about the quicksort? Well, the partition. Okay, and for what does the partition do? For the partition, we have a pivot, and then the pivot will be put into the middle or somewhere around the middle, hopefully. And then we are going to have two sublists. And what are the interesting facts about those two sublists? So for the lower part of the sublist, those values are all smaller or equal to the pivot. And for the upper sublist, and those values are all greater or equal to the pivot. So how does the partition related to the selection problem? Okay, let me ask another question. When we do the partition, and then we are going to do the recursive quicksort, right? And then how about the pivot? The pivot doesn't move anymore. Okay? And then that is the important thing about quicksort. Even though we have a very skewed partition, we may have only two values on one side, and then the rest of the values are all on the other side. It doesn't matter. If we are considering the selection, we do have one thing. That is, for the pivot, it's already at the right place. And if you know there are two values on one side, and then the pivot is the third value. So can we say now whatever the pivot value is, that is the third order statistics. Okay, so that's the cool thing about the quicksort, and we are going to use the idea of the partition, and we are going to do a slightly different, but we are bringing in the idea of the partition into the selection problem. Let's say, let me go to my drawing board and say, well, to start at the very beginning, let's assume that we just have 100 values. So the P, which is the lowest index, will be 1, and then the R, which is the upper bound of the index, will be 100. Okay, and then we are doing the partition and on 100 values, and then P is 1 and R is 100, and after that, let's just say Q is 35. Okay, so it's kind of a okay-ish partition, and then we can say that whatever here, that is the 35th order statistics. Okay, and then let's say we are trying to find the 50s. Okay, we are trying to find the 50th order statistics, and now what kind of information do we have? Okay, and we can say for the 50th order statistics, we are gonna only look at this side. Why? Because this is 35, and then we have 34 values on the lower sublist. We don't have to look at them anymore. So, and then we are gonna shrink or tighten the search space. We are gonna put the P here, and then P is the 36. Right? And then we are going to only search in this area, and then since we are going to start from the 36 and all the way up to 100, how many values are there? We have only 65. And then if we are looking for the 50th order statistics, and then we are starting from the 36, and then what is the new number of the order statistics we are looking for? We are going to do a 50 minus 36 equals 14. So in the new search area, from the P as 36 and R as 100, now we are looking for the 13th order statistics only in this part. Okay, so for the other part, we can just throw that away. So we are still bringing in or borrowing the idea of the partition, but the difference is in the quicksort, we have to sort both the in the quicksort, we have to sort both the lower half and the upper half after the partition. But now, depending on the other statistics we are looking for is in the lower half or the upper half, we only have to touch one part, and for the other part, we can throw that away. Okay, so that's the idea of the randomized selection. And well, if you check the code, and you can see we are trying to well, if the lower index and the upper index, they are the same, and then that is the value we are looking for. And otherwise, we are doing a partition, and then the k will be the new index we are looking for. And then if we find that if I is exactly the k, which means we are just looking for that index, and then we find that it is right on the pivot, and then we are gonna return the value on the pivot. And otherwise, depending on the other statistics, is on this side or on this side, we only have to do the recursive randomized selection on one side of the sub dataset. So, well, you may feel this code should be kind of similar to the quicksort. So the next question is, what is the time complexity, right? So, well, before we move on, and then let's work on this example to make sure that we understand that. Let me grab those values. I'm going to do a delete. Okay, and then let's use the old school partition, and then we are assuming that we are using the first value as a pivot. So the pivot is 5. And then we have really two subsets. Well, let me just do that in an easy way. So I'm just putting two bags of values. Okay, so we have 15, this is on the upper half, and then we have 8. 3 is on the lower half, and then 7. We have 1. We have 9. We have 10. We have 6, 7, 12, 14, and 2. Okay, so in this case, and after this round of the partition, and then we know that 5, what is that? This is the fourth order statistics. That's guaranteed. Why? Because there are 3 values on the lower side, so 5 is the fourth. So if we are simply looking for the fourth order statistics in this set, and then we are lucky we have already found that because the pivot itself is the fourth order statistic. And say if we are not looking for the fourth order statistics, we are looking for the 6th order statistics, and then what are we going to do? This equivalent to 6 divided by 4 equals the second order statistics only in this dataset. Okay, and then we have only need to solve one sub-problem. The sub-problem is how do we find the second order statistic in this bag of the data. So we are going to do another partition, and depending on our luck, we may have to do several recursive calls of the selection algorithm, but eventually we are going to find it. Okay, so let's move on and talk about the time complexity. So, well, do you guys still remember what is the worst case of the quicksort? So for the worst case of the quicksort, we have the pivot, and then there's no value on one side. All the values are on the other side. And then what is the time complexity? So every time we can only reduce the problem size by 1. So that Tn will be Tn minus 1 and plus On. What is the On, by the way? The On is the cost of the partition, right? So in this case, well, we have the Tn equals Tn minus 1 and then plus the On for the partition cost. And what is that? That is the On square. And then for the randomized selection, that's exactly the same thing. This means if you're unlucky, we always pick the lowest value or the smallest value as a pivot, and then this randomized selection is still an O n square algorithm. And let's talk and then consider the sorting. Well, if we just want to do a sort and then we find any other statistics we want to find, and what's the cost of a sorting algorithm? and we can do n log n sorting, right? So O n squared is even worse than n log n sorting. So in the worst case, the randomized selection algorithm will be even worse than a sorting algorithm, and then pick which error value we are looking for. So let's see a better case. It's not a super good case, and let's assume that we are doing the 90% to 10% partition all the time. And then if we are also assuming that the value we are looking for is always at the larger part of the partition. So the value we are looking for is on the 90% part of the partition. So every time we can reduce the problem size by 10%, we still have a 90% of the size of the problem to be solved. And then we still have an ON. And what is that? And that is the master theorem, the case 3, and then that is an ON. So isn't it good? Because it's the difference between this version of the algorithm to the quicksort we have already learned is, for the quicksort we have to sort both parts after a partition. But in the randomized selection, we only have to touch one side. Even though we are assuming that we are always touching the larger subset of the problem, we only need to touch one side of the problem. Okay, so in this case, it's better than the sorting algorithm. Okay, and then how about the 99 to 1 split? And the answer is the same. And we just need to change this number, but still this is a ON algorithm. Okay, and then we want to do an average case. We want to give a proof similar to what we have done to the quicksort. Okay, and in this case, we are assuming that the partition could be anywhere between a 0 to n-1 partition to a half partition to n-1 versus 0 partition. So that's the reason we are doing a k here. When we are doing a split, and then we are assuming that there are k values on one side, and then another n-1 minus k on the other side. And then we are also assuming that we are always going to the larger larger part of the sublist to find the ice order statistics. Okay, and then we are going to start from here, and then for the theta n, that is the cost of the partition. And then since we are doing the max here, and then we are gonna only use half of the data set, because if we do from the 0 to n, and then we have to pick whichever is the larger, k or n minus k minus I. So if we just start from half of that, and then we always gonna pick the upper half. So in this case, we are gonna start the k from n divided by 2 and go all the way up to n minus 1, and then I'm doing a 2 here, but it is guaranteed that we are getting the upper half, whichever side has the more values. Okay, and then as we have discussed, if we can prove that in the 90% versus 10% partition, it is still a ON algorithm. So we are confident the average case, it should also be an ON. So we are going to do a substitution. We are going to substitute this Tn with a linear time, and then we are going to prove that the entire Tn is also a linear time algorithm. Okay, so sorry, this is kind of annoying again, but I'm gonna go through that very quick. If you have already understand the proof of the average case of the quicksort, this is an easy case for you. Okay, so we started from here, and then what happened here? So we are substituting the Tn to the Ck. So we are doing a substitution because we know, or we are very confident that this this Tk is going to be a linear time. So we are just substituting the Tk with the Ck. And then what is this part? Well, first we are trying to extract this C out because this C is a constant. And then for the sigma, or for the sum from the n from the half n to n minus 1, we are splitting that into two parts. So the first part is the sum from the k equals 1 to k minus 1, and then I'm subtracting the lower half, which is the sum from the k equals 1 to the k n minus 2 half n minus 1. And then you will see this is a Gaussian series. This is another Gaussian series. So we are just applying two Gaussian series there, and then we are trying to massage the data a little bit, and then we have this version. Okay, so this is not really too bad. And so since this is what we have right now, and after that I want to multiply this c in, and then this c divided by 2 also in, and then we have this, and then I want to massage this a little bit, and eventually for this minus c and then plus 2c, and then that is minus 2c, and eventually I have the cn, and then for all the rest of them I put them into this parentheses. So this cn, what is that? That is a constant time and multiply n, right? So that's linear to n. And what is this part? So we have a linear n, and then plus a constant, and then minus a linear n again. So this is a cn, and then a minus something linear to n as well. And this means this is smaller or equal to cn when c is a constant number. So this is a proof that the tn is smaller or equal to a cn. This means the Tn is also a linear algorithm in the average case. Okay, so this is the part of the for the randomized selection algorithm. In this algorithm, we borrow the idea of the partition from the quicksort. And well, the difference is in the quicksort, when we have the pivot and then we have two parts, we are going to sort two parts at the same time. And for the selection, if we have the pivot, and then we only have to decide the other statistics we are looking for is in the upper half, or it's in the lower half, or in the upper half. Okay, so that's the part for the randomized selection. And remember, in the worst case, it is still an n square. But well, usually this algorithm will be good enough. In the next video, I'm going to talk about a worst case linear time selection. This algorithm is really way too tricky, and then I'm not going to challenge you guys to code that, but this is still a very cool algorithm I want to show you. Okay, I will see you in the next video.